Good afternoon to all. Welcome to this uh, fourth doubt clearing session of the course Engineering Thermodynamics. So the way we have continued our doubt clearing session, in the same way I'll go today also. So I'll first speak the question, whatever has been written in the Excel sheet, and then I'll actually try to answer that. Okay. So the first question which I'll be taking for today is question number 76 on our Excel sheet, because till 75 I have already taken up in the earlier clearing sessions. Okay. So the question is there any error coming when some expansion of gas in mercury column to measure pressure of that gas, some volume increase, that's why we take pipe of mercury column. So I think this question is related to the mercury in glass type thermometer. So in case of mercury in glass type thermometer, we are not having any relation with the ideal gas equation. So that's why pressure will not be, change in volume will not be causing any error. Let me just once again explain the concept of mercury in glass thermometer. So what we have in case of mercury in glass thermometer, we have a glass tube. Okay, so we have a glass tube, and in this glass tube, we have one small capillary. So here we have some bulb, and above that bulb, we have one very thin tube. That tube we call as nothing but our capillary. Okay. Now what we do, we take certain mercury level. Okay, so mercury is mainly contained inside this bulb. Now depending upon the value of the temperature, what we will be doing, this media we will be placing over here, our medium, for which we want to actually measure the temperature. So once we are placing the medium over here, if medium is having high temperature than that of thermometer, in that case what will be happening, there will be transfer of heat from the medium to the sensing part of the thermometer. So because of that, whatever the fluid we are having inside, so mercury we have inside, we will be having actually nothing but increase in temperature of the mercury. Okay, so now we know that if the temperature is increasing, then there will be some volumetric expansion within the mercury. So because of that volumetric expansion, now what will be happening, the level of mercury will be actually rising in this tube. Okay, so now once the level of mercury is becoming constant, it means my thermometer has come in thermal equilibrium with its medium. So now corresponding to that, we will be having nothing but fixed level in our thermometer capillary, fixed level of the mercury, and that level of the mercury is actually related with the temperature value. Okay, so is this point clear? Because here we are only having the principle of thermal expansion. So that's why though we are finding that okay, mercury is expanding, its volume is changing, but that is what actually our basis for measurement of temperature. So is this point clear? Deepak Gupta asked this question. So is this point clear to all?
Yes, sir.
Okay. Then we have next question. Why we have taken the rotational energy for x-axis to be 0? So let me explain this concept. So what I have told you, that what I am doing, I am considering my oxygen molecule, and for this oxygen molecule, while I have considered my coordinates as this is my x-axis, this is my y-axis, and this one as my z-axis. Okay, so now we know that our rotational kinetic energy is nothing but equal to half I into omega square, where I is nothing but our mass moment of inertia. So what is I? I is nothing but mass moment of inertia. So now what will be happening about x-axis? If you see, what we are saying, that x-axis is actually exactly coinciding with the molecular position. Okay, so in that case, what will be happening? The mass of the molecule will be exactly coinciding on the x-axis. So because of that, in our fundamental definition of mass moment of inertia, we have mass into r square, okay, where r represents the distance from axis of rotation to the location of the mass. Okay, so as our molecule is actually exactly coinciding with the axis of rotation, so because of that its moment of inertia is equal to 0 and we will be having negligible rotational kinetic energy. Is this point clear? Question number 77. Khushi Baghel.
Hello, sir.
Yeah, please.
Sir, I'm Deep Gupta. Sir, uh, uh, before that you have explained, sir, my question is that suppose a container that having some gases that have some pressure, that after this we use mercury tube for measuring this pressure for
Okay.
for difference in height of the mercury column. Huh?
Yes. Yes.
Sir, sir, the gas from mm, that to go gas from container go to some gases go to mercury column. That's why, sir, volume of the gas increases.
No,
Huh?
no, 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 no. There is no physical transport of the gas into mercury. What
Sir,
happens?
sir, sir, to how will be difference in uh, uh, height of the column?
What will be happening? Say if thermometer was at ambient temperature. Okay. Let us consider thermometer was at 25 degrees Celsius. So now the mercury inside the thermometer will be at 25 degrees Celsius. Now let us consider our medium for which we want to measure the temperature. That medium.
Sir, I'm not measuring temperature, sir. I want to ask to measuring pressure.
No, no, no. This we are using for measuring the. So that's why you have to like clarify your point. Mercury in glass thermometer is used for measurement of the temperature, not for pressure.
Sir, we can use to measure pressure also, not that for difference in mercury height column. Say,
So that is a difference actually. Okay, when we are having mercury in a tube and we are physically allowing the gas to move, that we call as manometer.
huh?
So that we call as manometer. So I think I have now then not clearly understood your point. Let me give you, let me draw the system for manometer. So this is what we are having a gas, okay, and then we have one U tube over here,
Yes,
something
sir.
like this. And then inside this U tube, we'll be now having mercury. Now, can you please repeat
Yeah,
the
yes,
question?
sir.
What you want to ask?
Sir,
Yeah.
sir, I want to ask, let's me suppose that we have container in which gas or after we use to measure pressure of that gas, we
Okay.
use U tube in which
Manometer.
mercury filled.
Okay.
Then we connect from the container.
Yes.
Then we get some height difference. Gas
Okay.
from the sir, gas from container. Some gases goes to mercury column to
Okay.
for difference height. Sir,
Okay.
I want to ask that we get some error na, sir, that
Oh,
measuring
understood.
pressure.
Understood. I understood. You are saying the volume will be changing inside the gas container. Okay.
Yes, sir.
So
Yeah.
basically, when we do this for the measurement, what happens? The tube diameter is very small in comparison to the size of the container. So that's why whatever the volume will be going inside the tube, that will be negligible in comparison to the overall size of the container. So that's why error encountered will be almost negligible.
Yeah, yes, sir. Sir, that is why I have written that also we have to take thin thin pipe, na that.
Yes, yes, yes. Thin pipe. So sorry, I have not read your question fully. So I thought that you are asking to the thermometer. Okay, but now I got your question. So there we used to go for very thin pipe. Okay, but Once again, its thickness should be larger than the capillary length scale. Otherwise, we will be having dominance of surface tension. Okay.
Yeah, surface tension also effect.
Yes. So we have to consider a pipe size so that surface tension is not coming into picture.
But sir, we have also seen surface tension of mercury is for glass tube.
Sorry.
Surface tension of the mercury is low for the glass tube.
Yes. That is one of the reason. That is one of the reason. Many times we go for very small tubes also. Okay. But as we don't always use the mercury as manometric fluid, many times we use water also, alcohols also. So that's why in general I am giving that statement.
Thank you.
Okay. So second,
Sir?
yeah, Khushi, your question is answered. Hello. So are you all satisfied with the response of question number 77, or do I need to explain it again?
Excuse me, sir.
Yes.
Sir, actually, I didn't understand question number 76. Although the doubt has been clarified, but can you please explain the question and answer once again?
So the question was, when we are connecting a manometer to a container of gas, some amount of gas is actually transferring to the tube. Okay, so it is going inside the tube of the manometer. So will there be any effect of change in volume of the container on the pressure? Because some amount of gas has entered inside the tube, so obviously there is some volume loss in the container. So how much error is encountered because of that, if there is any error? So my answer is that we are having very thin tube, so that the volume entered inside the pipe is negligible in comparison to the volume of the container. Okay.
Okay. Thank you, sir.
Okay, question number 77, I have explained already why we have taken rotational energy for x-axis to be 0. So I answered it again. Now the response is clear, or still you are having confusion?
It is clear, sir.
Okay, so now then I am going to question number 78. Please tell that vibrational energy will be 0 or not in monoatomic gas, and please explain about nuclear energy changes inside the atoms. Okay, so nuclear energy changes I am not going to discuss in very much details. Why? Because that is something which comes into picture when we are having nuclear fusion and fission reactions. So that is not the part of this particular course. So that's why I'll not be taking it over here. But what I'll do, I'll just explain you about the concept of vibrational energy. So vibrational energy is nothing but when molecules are at any location. So for example, if we have a number of molecules, so it is not the case that molecules at their location will be always remaining stationary. So they will be having the opportunity. For example, if I take oxygen molecule only, so it will be having opportunity either to like move in this direction. Okay, then this oxygen molecule will be having opportunity either to go like this, or it may be the case that one of the molecule is actually traveling towards left and another molecule is traveling towards right. So all these motions which will be there at the specific locations of the molecule, these are particularly referred to as the molecular vibrations, and these molecular vibrations also contribute to internal energy of the matter. Is this point clear?
Yes, sir.
Okay, then next question is, can the gauge pressure be negative? Yes, gauge pressure can be negative, because we know that at atmospheric pressure, the value of gauge pressure is equal to 0. So it means atmospheric pressure is nothing but P atm, atmospheric pressure in absolute, which is equal to 101.325 kilopascals. It is in gauge. If I write atmospheric pressure in gauge is nothing but equal to 0. Okay, so that's why what will be happening, as I have already told you, if we have any pressure which is less than atmospheric pressure, that situation we call as vacuum. And if we are having a situation of vacuum, then obviously we will be having value of gauge pressure as negative, because for atmospheric pressure we have 0 as the gauge pressure value. So for P less than P atmospheric, gauge pressure will be negative. Okay, then another part of the question is
Sir?
Yeah, please.
Sir, suppose we have a container and we have a piston. We have a piston over there which is movable, not fixed. Okay. So
Okay.
if we have any gauge pressure, suppose PG. So
Okay.
what we say that the piston will get force. Suppose inside the container there is a gas and the gas has some PG gauge pressure. So we will say that the piston will have a force in the upper direction.
So let me give an example. For example, if I take a situation, I have this cylinder, okay, and here I have say piston, okay, and then I have say W weight, and this W weight is such that it is giving me a gauge pressure of 0.5 gauge, okay. So it is nothing but 0.5 gauge pressure. Now outside say we are having our ambient. So if outside we are having ambient, our pressure will be nothing but 0 gauge. Okay, so now inside pressure is 0.5 gauge, which is greater than 0 gauge. So that's why obviously we will be having the displacement of the piston in upward direction. Is this point clear?
This is the significant. This is the physical significance when we have gauge pressure, right? So
Yes.
This time this is positive. So what is the physical significance of negative gauge pressure? How can we understand its physical significance?
Negative means piston will be moving inside. Okay.
Inside, that is, it has a suction pull.
Yes. So for example, if I take once again same piston cylinder arrangement, then I have this cylinder, then I have some gas inside. Okay. Now obviously what will be happening? Spontaneously this process cannot take place. Okay, because inside pressure has to be low in comparison to the pressure of the surrounding. So this thing spontaneously cannot take place, because fluid always flow from high pressure to low pressure. So what we have to do, we have to additionally connect one vacuum pump over here, and this vacuum pump will be actually creating suction inside the gas. So because of that, now piston will move in the downward direction. Is it okay?
Yes, sir.
Okay, so now then I'll go to question number 80, U vibrational and how it's 3 translational and 2 rotational. Okay, so let me once again explain it for oxygen molecule. So this is also 3 translation and 2 rotation is only applicable for oxygen molecule. If our molecule is changing, it may have different degrees of freedom. Okay, so let me once again take the example of oxygen molecule. So one O and second O, these are bonded together. Now, if I fix the coordinate system, something like this, X, Y, and Z, now what will be happening? If this whole molecule setup I consider like this, so now this, whatever the thing I have considered, this black colored encapsulation of our entire molecule. So this black colored encapsulated portion can go like this after some time. So now you can see it has translated also in X direction, it has translated in Y direction, and if it is, I draw it some off the plane, then obviously it will be having some translation in Z direction. So our molecule can translate along the 3 principal axes. Okay, and rotation, how it is coming into picture. So obviously one rotation we will be having about X-axis, and the rotation about X-axis will be having the 0 mass moment of inertia. So that's why I have already specified in earlier slide that we will be having rotational energy in X direction as 0. In Y direction, if our molecule is oscillating or rotating in say if our molecule is rotating in XZ plane. Okay, so if our molecule is rotating in XZ plane, this is my Z, this is this is my Y, this is my Z, and this is my X. So if initially my molecule was in this orientation, and after some time, if molecule is taking this particular orientation, it means this molecule is now rotating in xz plane. Okay, so obviously it will be having some rotational kinetic energy about the y-axis, and if similarly molecule rotates in y, if it rotates about the x and y plane, then it will be having some rotational kinetic energy about z. And if it rotates and spin about x-axis only, so because of that spinning about x-axis, it will be having actually zero rotational kinetic energy, because its mass moment of inertia will be zero. So is this point clear?
Yes, sir.
Okay, then next question is, please tell why you took kinetic energy 2 times, one for macroscopic and other for molecule. Yes, this is a good question. So let me give you one example. Say I have some quantity of matter, some quantity of, say, some gas or liquid inside this container. Okay, so now the first thing is, if I am moving this container, say at t equal to t1, this x1 is the position of this container. Now after some time, let us consider that this container is moving. So after some time, say t equal to t2, the new position of the container is x2. Then after some more time, say t equal to t3, its position is x3. So now you can see at macroscopic level, the container is changing its position with time. So if it is changing its position with time, it means it is possessing certain amount of velocity. Now if I take m as mass of the container, so obviously what we will be having, we will be having some kinetic energy which will be equal to half into m into v square at the macroscopic level. Okay, so why this container is moving from one location to another location? It is nothing but changing its physical state. Okay, now if we talk about the medium inside, so inside I will be having number of gas molecules. Okay, so while it is changing the location from a physical state from one point to another point, every time we are having the same number of molecules inside, and obviously because it's a gas, it's a fluid, so molecules will also be having some collision, some motions within the container. Okay, so because molecule in case of a gas will not be remaining at same position, so at the molecular level, molecule will try to move from one location to another location. So that's why these molecules will be also possessing some amount of energy, some amount of molecular translational kinetic energy, which will be nothing but equal to half into molecular mass into velocity of molecule square. Okay, so these molecules are also possessing certain amount of molecular kinetic energy, and whatever the molecular kinetic energies we are having, this is nothing but giving rise to the internal energy of the system. Now let us consider that in my three different situations, at first point also my temperature of the container is T1, second time also temperature is same, T2 equal to T1, and third time also it is T3 equal to T1. So it means in all these three different locations, what is happening, our physical state of the system is changing. So that's why the content of kinetic energy, macroscopic kinetic energy, will be actually, if velocity is different during the successive time intervals, then that may change. However, as the thermodynamic state of the system is actually almost same, so because of that, what will be happening, whatever the internal energy content we are having inside, which is contributed due to the molecular translation, that will be remaining same. So now is this point clear? Are you able to differentiate in between molecular and macroscopic kinetic energy?
So what is the
Sir,
value
so-
of m in this question? Does it also include the mass of gases in macroscopy level, or mass
Yes.
of container is only there?
It also includes the mass of gases in macroscopic level.
Sir, so can we say that the internal kinetic energy is due to Brownian motion?
Yes, that point is correct.
Okay, sir.
So, and that part actually we are calling as nothing but, as we are saying, it is contributed in terms of the internal energy of that system. Okay.
Okay, sir.
So yeah, like it's nothing but that your global position of the system is changing, and while the global position of the system is changing, then locally you are having every time some molecular motions. Okay. So can I move to next question?
Yes, sir.
Okay. Okay, so next question is, please tell us what was the question? Up to which question I have covered?
Sir, you have covered up to 81 questions.
Oh, up to it. Okay. So next question is, can you explain the U atom part again? Okay. So in case of U atom, what will be happening? Like we know the structure of the atom, we will be having some positively charged proton at the nucleus. Then we will be having some negatively charged electrons, which will be orbiting around this nucleus. At the same point of time, each of the electron will be having some spin motion about its axis. Okay. So all these kind of motions of the electron will be contributing certain amount of energy. Then we have binded the, so if you see, electrons are at certain specific distance from the center. Okay, so it means in between this positively charged nucleus and the electrons which are orbiting around the nucleus, they are having some binding force which is actually holding the electrons in their particular location. So all these type of the forces which are there within the atom and are responsible for particular configuration of the particles which are inside the atom, these contribute to certain amount of energy, and that particular energy is actually considered as U atomic contribution in our total mention of internal energy. Is this point clear?
Sir, so it also includes the electron proton attraction or
Yes.
repulsion
Yes,
forces, all
yes.
that.
Yes,
Okay,
everything which is actually part of the which is happening within the atom, that every contribution, whether it's potential binding, it's electron motion, etc., everything is actually contributed inside that U atom. Okay.
Okay, sir.
Then next question is, in absolute temperature, T is proportional to P, therefore T equal to A into P. But why we have specified T equal to A plus BP? Okay, so let me once again answer this question, though already I have answered in the previous doubt clearing session. So yes, the idea is clear that temperature is proportional to pressure, but we are not knowing. So we have started with ideal gas thermometer, and while we have started with ideal gas thermometer, we were measuring our temperature in degree Celsius, and this degree Celsius is not a absolute scale of temperature. It is not absolute scale of temperature, because we considered 0 degrees Celsius corresponding to ice point. Okay, corresponding to ice point, but we may have situation where temperature can go below ice point. Okay, so that's why corresponding to absolute pressure, corresponding to P absolute, whatever the temperature scale we have considered, that is not giving us the 0 value in degree Celsius. So that is something which is not giving us. Okay, corresponding to absolute pressure means corresponding to pressure tending to 0. we are not having T tending to 0 degrees Celsius. So that's why we have to use some intercept while specifying T equal to A plus Vp. However, later on we found that corresponding to absolute pressure, we have nothing but 0 Kelvin temperature. If we see the Kelvin scale, if we consider our temperature in Kelvin, then we can directly say temperature in Kelvin as nothing but V times P, for which our A intercept will be 0. Is this point clear?
Yes, sir.
Okay. Then I am now moving to next question, which is, can you explain the quasi-static process again? Okay, let me explain once again. So what I am doing, I have taken a piston cylinder arrangement. And in this piston cylinder arrangement, actually, I want to specify certain W amount of weight, but that I'll be taking summation of small weights. Okay. And let us consider these small weights are nothing but W1, W2, W3. So something like that, very small weights we are having. And let us consider initially my pressure is P1, volume is V1. Now, if I plot this process on PV diagram, this will be my start point, point number 1. Now, what I have done, I have removed one of the weights. So this weight I have taken out. So while I'll be taking this weight out, what will be happening? My weight on the piston has slightly decreased. If weight on the piston has decreased, inside pressure of the gas will be more in comparison to the pressure which is acting because of the weight, and in order to balance the pressure, our piston will slightly shift in upward direction. Okay, and now we are having nothing but remaining weights over here. So it means we have got some new state P1 dash, for which P1 dash is slightly less than P1, and we have got new volume V1 dash which is greater than V1. Okay. Now, because the amount of weight we have removed is very small, so that's why this process will happen at very slow pace, and we will not feel inside within the system that we are having any gradient of pressure. Whatever the pressure change has to happen, that pressure change will be so smooth that we will not be finding any change of the pressure within the system. So because of that, we'll be able to determine the next thermodynamic state. So which is I have represented with the help of a circle having slightly low pressure and high volume. Similarly, if I remove another weight, I'll be finding another state, another weight, another state. So like that, I'll be getting the number of stages unless or until I am removing all the weights. And finally, then I'll be having my final thermodynamic state as nothing but state number 2. So now this process from 1 to 2 has happened so smoothly that within the container, we are not having any variation of the pressure felt at any moment. Okay, so that's why at each and every intermediate locations, I can consider my system in thermodynamic equilibrium and I can specify its state. So if I can specify the state, I can nothing but obtain the path of the process by joining the intermediate states. Is this point clear?
Yes, sir.
Okay, the next is, can we plot a graph for irreversible process? Let us not take into account the irreversibility now. Yes, sometimes we plot the graph for irreversible process with the help of dashed lines that I have already told you. But in more details, we will be studying the concept of irreversibility after our discussion of the second law of thermodynamics. Okay. The next question is, how is internal energy and U internal are different? So U internal molecule is nothing but one contribution which is actually giving rise to the total internal energy of the system. Is this point clear?
Sir, so basically U internal is a component of internal energy.
Yes, that's a component of internal energy.
Okay, sir.
The next question is, please explain the sensible energy. Okay. Okay, so sensible energy, let me explain once again. So what we are having, sensible energy, if you go as per the definition of the sensible heat, when we add certain amount of energy and that amount of energy actually causes the change in temperature of the system, that particular energy we call as nothing but our sensible energy. Okay. Now we know from our kinetic theory of the gases that kinetic energy of gas molecule is nothing but equal to 3 by 2 times K into T. So it means my kinetic energy of gas molecules is associated directly with the temperature field. Okay, and temperature field is something which is directly associated with the definition of the sensible energy. So it means we are saying over here that if the temperature of the system is increasing, indirectly it is caused because of the sensible energy. So it means sensible energy is increasing. And if sensible energy is increasing because it is contributed because of the increase of temperature, so ultimately we can say that the kinetic energy of the gas molecules has increased. So is this point clear?
Yes, sir.
Then why such basic thing, zeroth law is called as law? Is there any point significant of zeroth law? So zeroth law is something which specifies the equality of the temperature, and temperature is one of the very, very fundamental property of the thermodynamic system, which is required to specify the state of the system and can be easily measured majority of the times. So that's why some hypothesis was initially given for the equality of the temperature, and that is actually, and that was very, very fundamental hypothesis. So that's why it has been given the name as zeroth law. Okay, it was preceded by the first law of thermodynamics. Okay, the idea is only to specify equality of the temperature, which is a very, very fundamental property in our thermodynamic systems. Okay, is this clear, Subhan?
Yes, sir.
Okay, then we have next question. What is the difference between U external molecule and U potential? Okay, so this is a good question. Now, once again, the idea is when we have the potential energy between the two molecules. For example, if I consider a molecule 1 over here and another molecule 2 over here, molecule 2. So now when these molecules will be coming very close to each other, they will be having some repulsive force, and when they are far apart, they will be having, means then they are far apart, then there is no interaction, and when they are close enough to each other but not very close, in that case they will be having some attraction forces. Okay, so it means the interaction between the molecule to molecule is something which is considered as UEXT molecule. Okay, then comes the concept of U potential, and this particular U potential I have taken within the broad component U internal molecule. So in case of U internal molecule, what will be happening? For example, if I take methane molecule, so in case of methane, I will be having 4 hydrogen atoms bonded to methane. So if I have to break this bond, then I have to spend certain amount of energy in order to break the bond in between carbon and hydrogen atom. So that particular internal energy which is required to change the atomic structure, or I should say which is required to change the molecular structure, not the atomic structure, the molecular structure. Okay, that particular energy within the molecule we call as U potential. So anything which is from molecule to molecule, that is U external molecule, and anything which is within the atoms of a molecule, that we call as U potential, and that comes in the category of U internal molecule. Is this point clear?
Yes, sir.
Okay, so is there any other question?
Sir, I had a question regarding the assignment.
Yeah, please.
In the fifth question, everything is in terms of inches. Do we
Okay.
have to convert all the densities and everything in inches? Because by doing that, I'm not getting 18 point, whatever the answer is.
So you can follow any system. Either you can convert to SI units or you can convert to this one, MKS units. Okay.
Okay, so after getting final answer, again convert it to check if it is 18 point, whatever
Yes,
the
yes.
answer is.
Yeah, that you can do. That you can do. Okay. So just be consistent with any type of units and then finally convert your answer.
Okay, sir. Thank you.
Okay. Any other
Sir?
question? Yeah, please.
Sir, like you said that U internal is a component of internal energy. So can be classified under any of the 4 type of energies that we learn, like into sensible, latent, any one of them?
Yes, we have specified. Yeah, we have specified that if our atomic structure of the molecule is changing, it means if an atom is changing, actually it is losing some electrons. Say there is like in case of nuclear fission and fusion reaction, then that energy, particularly the atomic part of U internal molecule, comes under nuclear energy. Okay, and if we talk about the breakage of bonds, for example, methane and oxygen are interacting and they are forming carbon dioxide and this one water. In that case, what will be happening? The bonds in between the different atoms are actually changing and they are changing the overall molecular structure, because methane molecules has converted into water molecules or the carbon dioxide molecule. So that part is also U internal molecule. So there what we will be saying that that particular part is actually contributing in chemical energy. Okay. Is this point clear?
Yes, sir. Yes, sir.
Ujjwal,
Sir.
yeah.
Sir, can we consider rotational energy of a molecule in U translational, or it is only confined to U intermolecular?
So basically, if we are having rotational energy, so mainly we are confining it to U internal molecule only when molecular motions are about their molecular axis. Okay. If we are having a situation of rotational flow where we are having bulk rotation of the molecules about an axis, for example, in case of swirl flow, we get in case of vortex induced fields, there we have to consider separately rotational energy as half I omega square about the bulk axis where rotation is happening.
Okay.
Ujjwal is asking, can you discuss question 4 of assignment here? It will be good if you are speaking out your doubt in question 4, because I don't have the assignment at present with me. Ujjwal, can you please specify your doubt, because I don't have at present assignment with me.
Sir, I have the assignment open. Do you want me to read it?
Yeah, you can read the question.
Okay, just a minute. Consider the system shown. If a change of 0.7 kilopascals in the pressure of air causes brine-mercury interface in the right column to drop by 5 millimeters in the right column, and the pressure in the brine pipe remains constant, determine the ratio of A2 by A1.
So that's I think very simple question. It is based on the conservation of volume only. Okay. So whatever the volume will be shifting, transferring from left side to right side, that volume will be reflecting certain amount of height. Okay. So if you apply the volume conservation and if you do volume as area into height on both the sides, you will be finding the ratio of areas. Is this point clear?
Yes, sir.
Okay. So if there is no other question, then I'll end up this session over here. Or is there any other question also?
Sir,
Yeah, please.
attend the last doubt session. Can you please explain once more about the gauge pressure?
Okay. Okay, I'll explain. You can, though doubt clearing sessions are also recorded. So if you want to listen to doubt clearing session, you can see the recordings. I am uploading on Moodle also, but let me once again explain it over here. Okay, so in case you are missing some doubt clearing session, you can once again refer to the previous sessions. I am uploading these also. Okay, so what I have told you that while we are having the pressure, here we take pressure along ordinate, and what I am saying, corresponding to zero magnitude of pressure, we say nothing but our absolute vacuum. Okay, now let me consider that my atmospheric pressure is somewhere over here. Now, if I measure the value of pressure at any point with reference to the absolute vacuum, that I'll be calling as P absolute. And if same pressure I am measuring with reference to the atmospheric pressure, considering atmospheric as my reference, then obviously I'll be calling that pressure as nothing but my gauge pressure. Okay, and the pressure up to this point is nothing but my P atmospheric. So from this particular thing, you can see that my P absolute is nothing but equal to P atmospheric plus P gauge. So it means gauge pressure is nothing but when we are measuring the pressure with reference to the atmospheric. So this equation is applicable for positive pressures. So positive pressures means when we have pressure greater than P atmospheric. If our pressure is less than P atmospheric, in that case, what will be happening? My actual point where I want to measure the pressure will be somewhere over here. So any pressure below atmospheric actually considered as vacuum. So I'll be saying this my P absolute, but this is my vacuum pressure. Okay. Now if same pressure I measure with reference to atmospheric, now corresponding to atmospheric, because we have zero gauge. So in terms of gauge, this pressure will be negative pressure. So this will be my now gauge pressure in vacuum. So if you try to relate over here with atmospheric pressure and absolute pressure, you will be finding that P absolute in vacuum is nothing but equal to P atmospheric minus P gauge in vacuum. So is this point clear? Shubham? Yeah, please.
But what's the requirement to define such a new gauge pressure, sir? What is the requirement for doing so?
The requirement is that because it's not at all possible to achieve absolute vacuum. Okay, so that's why while we will be calibrating our devices, what we have to do, every time we have to use some external means, for example, vacuum pump, etc., in order to calibrate our devices. So that calibration of the device becomes fairly complex. Rather, if we start our situation with reference to the atmospheric pressure, and for atmospheric pressure, if we assign the scale of 0, we need not to employ any external device for calibrating, any external arrangement for calibrating our devices. Only we need to subject our gauge to the pressure which we want to measure. Is this point clear? Okay, so now then I'll end up this session over here and we'll take up the further queries. Yeah, please.
Sir, considering microscopic and microscopic velocity, when
Yes.
container is moving in positive x direction,
Yes.
and so what about molecules moving in minus x direction?
So obviously for molecules, what we will be doing, molecules will be having some positive velocities, some negative velocities, so their kinetic energy will randomly oriented. Okay, for molecules, the kinetic energies will be randomly oriented, and these molecular energies will be giving us some bulk property which is called as nothing but our internal energy. Okay, so that's why as a whole, as a bulk, we specify only the internal energy magnitude. We don't specify individually the magnitude of individual kinetic energy of each and every molecule. Okay, so that is for our understanding that what are the different components of which our internal energy is actually comprised of. Is this point clear?
Yes. Yes.
Okay. So is there any other question? Okay, so now I'll stop at this point and we will see